Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last class, we discussed about deflection of open and closed section beams, and we have seen how the deflection can be solved for open section beam which are subjected to booms and subjected to the vertical shear load. Now in the present session, we are going to see some more problems on how to calculate shear flow or shear center, shear flow distribution, either open section beam or closed section beam. So we are going to see a problem like this. So the learning outcomes in this module are students are able to solve problems on shear center. Let's try to consider this diagram. So the beam section shown in figure has been idealized into an arrangement of direct stress carrying booms and shear stress carrying panels. And if the beam section is subjected to a vertical shear load of 1495 Newton through its shear center, the booms 1, 4, 5 and 8 each have an area of 2000 mm square, and booms 2, 3, 6, 7 have an area of 250 mm square, and he is asking to determine the shear flow distribution and the position of shear center. Okay, so if you look at this problem, and by looking at the geometry of this the problem which is given, so first thing we need to understand here, it is the given section is symmetrical. The given section is symmetrical, so that you can substitute the product of inertia Ixy, that is equal to 0, and he has given a vertical shear load of 1495. So you can consider that Sy equals to 1495, and he said that it is acting through its shear center. So whenever the vertical load acts through the shear center, we can consider that the twist of the section is 0. That is, there exists no twist about that shear center. Okay, and since horizontal load is not given, you can substitute Sx equal to 0, and then the formula for shear flow distribution, since it is an open section, reduces to minus Sy by Ixx summation r equal to 1 to n Br Yr. You can consider this as equation number 1. Okay, and he has given the boom areas for 1, 4, 5 and 8. You can consider this as corner booms. So corner boom areas he has given it as 200 mm square, whereas the middle booms, that is 2, 3, 6, 7, and he has given the boom areas as 250 mm square. So the corner booms 200 mm square he has given, and then the central booms and 250 mm square, and he is asking to calculate the shear flow distribution, and thereby he is asking to calculate one more thing, is shear center. So since this is an open section, and the procedure will be straight away, but here you got the combination. You got two sections. One is 1, 2, 7, 8 is one section you have, and then other section is nothing but 5, 6, 7, 2, 3, 4. So this is second panel, and this is the first panel we have. So this is the problem, and therefore you have to calculate first its shear flow distribution, and once the shear flow distribution is known, and you can get the shear center, because we know that the property of shear center is that it lies on the axis of symmetry. So it lies on this horizontal axis of symmetry. It may lie anywhere. So it may lie here, or it may lie here, it may lie here outside, or it may lie here, it may lie here, or it may lie here, anywhere. So you can assume any one. Let's assume the shear center is acting at this point, and through that the 1495 vertical shear load is acting such that the twist of the section can be neglected. Okay, so by assuming like this, let's try to proceed in the problem. And the very first thing is you need to calculate the shear flow distribution, and then you have to go for finding shear center. Okay, so here you can see the formula that is given, that Qs equals to minus Sy by Ixx summation r equals to 1 to infinity r equals to 1 to n, and that is Br Yr. You can assume this as equation number 1, and in which Sy is known and Ixx you need to consider for the problem. And since there are 8 booms and all are symmetrical, when you consider this horizontal axis of symmetry, and above 4 booms are symmetrical to the below 4 booms, so that the calculation of moment of inertia, you know the formula for moment of inertia. So Ixx equals to summation of BR YR square. So boom area of respective boom and then its y distance from the centroidal axis. So since this is a horizontal centroidal axis, first if you look into this one, corner boom 5 and 8, it has got same area. Corner boom, that is 200. So you can write this as 200 boom area into its distance from here to here is nothing but, for 5 it is 40 plus next boom 6 it is 250. So 250 into, and this distance, in fact you have to write square, BR square. So 250 into 80 square, and then plus, this is Ixx we are writing. And if we look at it for 7, and again boom area for 7 is 250 and its distance is nothing but similar to that one, that is 80 square, plus the 8, that is corner boom, that is 200 and its distance is 50 square. And then the total upper moment of inertia multiplied by 2 for the below one, so that you are going to get the moment of inertia that is equals to 8.04 into 10 to the power of 6 mm power 4. So once you get this moment of inertia, you can take and substitute in equation 1, and by substituting Sy equals to minus 1495 and divided by Ixx, that is 8.04 into 10 power 6, and then you are going to get the shear flow distribution Qs is equals to minus 1.86 into 10 to the power of minus 4 summation BR/YR, that you can consider as equation number 2. Okay. And after this, then this is the distribution, shear flow distribution, what we got, shear flow distribution. And then once you get this distribution, you can find out the shear flow in the respective panels like 1, 2, 2, 7, 7, 8, and then 5, 6, 6, 7, 7, 2, 2, 3, and 3, 4. So that's how we calculate the shear flow distribution. Now, if you look into this one, first let's trying to calculate this 1, 2 and Q12. So when you try to write Q12, you have to consider the boom area of 1 and its respective y distance. So boom area of 1 is nothing but 250 and its respective y distance from centroidal axis is, since it is below horizontal axis and it is 50, so that you have to consider minus 50 as the y distance. So minus 1.86 into 10 to the power of minus 4. So boom area of 1 is 200 and its y distance from the neutral axis or centroidal axis is minus 50. You can substitute that, you are going to get 1.86 into Newton per mm. Next, once 1, 2 is done, and next you can calculate the other one, that is 4, 3. So 1, 2 is, this one is over. Okay, and next try to calculate for 4, 3. And if you try to calculate for 4, 3, so first minus 1.86 into 10 to the power minus 4, you have to write the boom area of 4 and its respective y distance. So boom area of 4 is again 200 mm and its respective y distance below the centroidal axis is minus 40. So you can substitute that, you are going to get 1.49 Newton per mm. Okay, and then Q12, once you calculated, it is equal to Q87, and then Q43 we calculated, it is equals to Q56. Okay, and next we are trying to calculate Q32. One after this 4.3, we are trying to calculate Q32. So Q32 is equals to minus 1.86 into 10 to the power of minus 4. You have to add the boom area, multiply boom area of 3 and its respective y distance. So boom area of 3 is nothing but 250 and its respective y distance from the centroidal axis is minus 80 below x-axis. So minus 80. But for Q32, there is a starting shear flow, that is Q43 of 1.49. What we got, that you have to add here. So that is, you have to add. So the 1.49. So when you do that, you are going to get 5.21 Newton per mm. So this is 5.21 Newton per mm, and this is also similar to get it. So Q32 is equals to Q67, 5.32. And next, what is left is the vertical shear flow, that is web. And for calculating the vertical shear flow for web, again you can consider minus 1.86 into 10 to the power of minus 4. And since you are calculating for 2.7, so let's try to write the boom area for 2, which is nothing but 250, and its y distance from the centroidal axis is minus 80, that we have written. So from here to here it is over. But since 27 is the common web for even this first section and the second section, then you have to add the open section shear flow. For example, if you try to consider this 1, 2, 2, 7, 7, 8, then the starting shear flow for 2, 7 would be 1, 2, that is 1.86, that you have to add first. And when you try to consider the second section, that is 5, 6, 6, 7, 7, 2, 2, 3 and 3, 4, we calculated 4, 3, we calculated 2, 3, and then we are trying to calculate 2, 7. For 2, 7 in the second section, the starting shear flow would be 2, 3, that is nothing but 5.21. Even you have to add that also, so that is added. So for the common section, common wall like this, so you have to add the shear flows, both the shear flows along with the formula for shear flow distribution what we have. So when you do that, you are going to get Q27 equals to 10.79 Newton per mm. Okay, so this is how we calculate the open section shear flows. So once the shear flow distribution is done, and our next thing is to calculate the position of shear center. Okay, so the remaining shear flow distribution follows from symmetry that we know. So the figure shows the complete the shear flow distribution that is shown here, and since this is open section, so we get the shear flows directly. So next thing to calculate the shear center, what we are doing here, we are taking moment about the midpoint of web 27. So this is web 27 and we are trying to take moment about this point. Okay, and since let us assume that the shear center is acting at this point and through which SY shear load is acting, and let us consider the distance of the shear center from web 27 as XS. XS is the shear center position. Okay, and since the given diagram is symmetrical about horizontal axis, so the shear center lies on axis of symmetry. So we are choosing this point as shear center acting, which is at a distance of XS. So our aim is to calculate what is that horizontal position of shear center, that is XS. Okay, so now let's try to apply the moment. First, the moment let's try to apply due to the vertical load and about this point O. Let's assume this point as O. So SY is the load and XX is the perpendicular distance. So you are going to get SY into XS as the moment up to this point, and which gives the anti-clockwise moment about point O. Okay, so the first thing is nothing but moment due to shear load. Okay, the next thing what we are going to write is nothing but moment due to shear flow. Okay, so there are a lot of shear flows here we have, that is starting from 1, 2, 2, 7, 7, 8 and 6, 7, 5, 6 and then 1, 9, 4, 3 as well as 3, 2. So it's very important to us that what are the shear flows that you need to consider. That is very important. Okay, so let's try to do one thing, that since you're calculating moment about this point O, and let's try to consider for the symmetrical section, and let's try to write the moment for upper half of the section, so that you can multiply by 2, so that it will give for the even for the lower half of the section. So when you try to write for the upper half of the section, and since this is 2, 7, and since it is passing through the same point where we are calculating the moment, it is not going to give any moment because the perpendicular distance is 0. Okay, so let's try to look into the other one. Okay, you can substitute here, and when you try to calculate this, you have multiply by 2 for the complete equation, and you are going to get XS, that is equals to minus 122 mm. Okay, so that means we assume the shear center here, but usually the shear center acts at the left side like this here. Okay, so that is how we try to calculate the shear flow distributions, and in fact for this problem you can calculate in other words also while you try to write moment, because here he has considered that the inclined walls, and instead of this length he considered directly as the horizontal length. So instead of that, what you can do here it is, and you can calculate this inclined wall length. So that is very important, so that again the moment you can consider the moment about when you consider this point, and you can consider this as 2AQ and 2 into area of that cell, and you can consider this area half into this 150 into 80 you can consider. into Q, that is Q43. That's very, very important here. And here also, what you can do here, it is you can take like this and you can add this one. Okay. So for this, if you try to apply for the moment due to 4-3 and the equation here, instead of the complete one like this, you can write in terms of the areas, so that even the inclined wall. So now here it is. So you can consider this area. So 2 into base, you can consider this is 150. So 2 into 1 by 2 area of this one, and then this is 80. 2 into A into Q you can write. So Q is nothing but again 1.49. Okay, or Q43 you can write what he has given, Q43. Okay, plus when you try to write the perpendicular distance, so the perpendicular distance from here to here, which you can consider here it as, you're taking moment about this point, so the perpendicular distance is 200 also you can add. Okay, so that is what here we have here, and we got that 40 into 200. Okay, so like that, instead of calculating directly like this, you can consider the areas, and then you can take about this point, you can take moment about this point O, and you can calculate the horizontal position of shear center, that is XS. Okay, so that's it from today's session. Let's try to meet in the next session with other problems on shear floor, shear center. So thank you everyone.